Thank you for the introduction. It's a pleasure to be here. So let me, why should I point this to work? It's not working. I use this. No, you destroyed this.
I did. I sabotaged it. I'm sorry.
Okay, so let me.
It should work now. The slide advance.
Okay, thanks. So let me tell you what my objects are. So I will be talking about a class of dynamical systems that is of number theoretic origin, and that might be interesting both from the number theoretical and dynamical point of view. So what are these systems? We start with a subset of integers, and we do a very simple operation. Namely, we take the set of all multiples of elements of this set. So this is the corresponding set of multiples, and then its complement is called the B-free set. So these are numbers that are not divisible by any of the members of B. So a few I cannot say this word. Few simple remarks. So the first one is that each set that is closed undertaking multiples is a set of multiples. The second one is that we'll usually assume that B is primitive. So no two elements divide one another unless they are equal. And the final one, for any set of multiples, we can find a primitive set B that generates the set of multiples. Okay, so it's quite clear that these objects can be interesting for a number theorists, so just by their form. So that's quite direct, and this happened already in 1930s. So this is where the history of this subject started. But they attracted also some attention from the dynamical viewpoint, and this is rather recent. And during my talk, I will concentrate on dynamical aspects. However, I will try to indicate some directions and give you some sample results showing why they are also interested. These objects are also interesting outside dynamics and how these things are related to each other. Okay, so let me give you two most basic examples of sets of multiples or B-free sets. So the first one are square-free integers. So our set B is the set of all squares of primes, and then the B-free set, these are just square-free numbers. So the characteristic function of this set is nothing but the square of the modulus function. And then we have abundant numbers. So we can split all integers into three classes. So we have abundant numbers, perfect numbers, and deficient numbers, depending on how large is the sum of all divisors. And it is easy to notice that the set of abundant numbers is close undertaking multiples. So this is a set of multiples. And so there is a primitive set B that generates all abundant numbers. These are so-called primitive abundant numbers. The same is true for the union of abundant and perfect numbers. So to get this primitive B, we need to add all perfect numbers to primitive abundant numbers. And one of the first questions in this subject was asked by Wesselhagen in 1929. So he wondered whether the density of the set of abundant numbers exists. The answer was yes. This was given independently by three mathematicians a year later. So a natural question occurred: is it true for all sets of multiples? Surprisingly, the answer was no. So Bezikowicz gave a whole construction how to get sets B whose corresponding sets of multiples or B-free sets do not have natural density. So the main idea behind it is that if you take the interval from t to 2t and you take the corresponding set of multiples, then the density of this set goes to 0 as t increases. Okay, so the density may not exist. However, the logarithmic density always exists. So this is one, I would say this is one of the strongest results from the 30s in this area. And in fact, we have more. So not only the logarithmic density exists, it is equal to the lower density of the set of multiples. And what is even more important, you can get there by finite or by periodic approximation. So you truncate your set B, you create a periodic set of multiples corresponding to this finite set, and you look at the density. So densities of periodic sets converge to the logarithmic density of your set you started with. And finally, Adler gave a somewhat complicated equivalent condition for the existence of density. So I'm not going to go into details here, but there is a characterization, and it is used every now and then in some papers. So if you need a criterion, there is one. Okay, so since there are plenty of subsets of natural numbers, there are plenty of different sets of multiples. The sets of multiples we could possibly get. And let me point out here some important classes that appeared already in this number theoretical context. So there is no dynamics involved so far. So first of all, we have Bezikovich sets. We are in this situation when the natural density happens to exist. A subclass of these sets are sets satisfying so-called Adler condition, which means that B is infinite pairwise coprime with a summable series of reciprocals. So for example, if B is equal to the squares of primes, we are here. Well, the density is then 6 over pi squared. And then kind of at opposite end, we have barren sets. So this is when the density of the set of multiples is equal to 1. So for example, you take a subset of primes with non-summable series of reciprocals and you get a barren set this way. And one more class that appeared back then were Todd systems. So Todd sets, so what are they? The condition is as follows. So you look at your set B and you pick an element. And you want to know if the logarithmic density of the corresponding set of multiples drops or not. If it drops, no matter what B you pick, then you say your set is Todd. So it's like each element is important from this density point of view. And there is a relation between barren sets and Todd sets. So B is Todd if and only if we won't find a rescaled copy of a barren set sitting there. So being barren somehow is like at the other end. It's as not Taut as you can be, yes?
So that's a question.
Oh, sorry. Does scaling a set have a nice effect on the logarithmic density?
Pardon?
So if you scale a set by some d, does that have a nice effect on the logarithmic density? Okay.
I don't understand.
Okay.
So is B uniquely determined by the set of multiples? Maybe you said this.
Wait.
Okay.
It will come up. All right, so let me introduce the language of dynamics so that I can actually start doing something. So let eta be the characteristic function of the B-free set. So we have a two-sided 0, 1 sequence. This is a point in the full shift over 0 and 1. And let sigma stand for the left shift. We have 3 subshifts associated to each such eta or to each subset B. So the first one is the B-free subshift. So you just take the orbit closure of eta under the left shift. The second one, x eta tilde, this is a hereditary closure of the B-free shift, which means that you take your B-free shift and you can replace ones by zeros. That's the operation you're allowed to do without falling out of your subshift. So in other words, if M stands for coordinates by multiplication, x eta tilde will be the image of x eta times the full shift by M. And finally, we have the largest out of these 3 subshifts, namely the B admissible subshift. So what is here? Here are all 0, 1 sequences, such that when I look at their support modulo B, there will be always at least 1 residue class missing. So there are these inclusions between these 3 shifts, and sometimes there are equalities, sometimes not. So there are examples of any configuration you want. And dynamical properties of these 3 subshifts turn out to be related to number theoretic properties of the set of multiples and B-free sets. So we have found like 3 main directions in which it can go. So there are patterns, recurrence, and combinatorics. So let me tell you a little bit about patterns. What kind of applications you can get once you do hard work in dynamics. Okay, so we go back to the example with abundant numbers. So the first fact about primitive abundant numbers, which is important here, is that this is a taut set. So in fact, there is more. The series of reciprocals is convergent. And this gives you not only that this set is taut, but also that the set of multiples will have, so the density will exist. And this, together with some dynamical results, gives the following. So we are looking at repetitive patterns. So we fix a finite subset of abundant numbers. We fix a finite subset of the union of primitive and deficient numbers. And we want to see if we will see the same pattern somewhere further. The answer is yes. And not only that we will see it infinitely many times, but also with positive density. So for example, if I want to see 5 consecutive deficient numbers, I will see it with positive density. I cannot see 6 because, well, 6 is not deficient. And another result is related to gaps between consecutive deficient numbers. So the question here is how far apart can the consecutive, let's say, triples of deficient numbers be? And we were able to prove that you will see them more and more apart infinitely often. Okay, so what about recurrence? I need some definitions. So we say that R is a set of recurrence if for every measure preserving system and for every set of positive measure, the set will return to itself at some point from this given set. So this is a very simple definition. We can complicate it a little bit. So what changes here for averaging sets of polynomial multiple recurrence is that we not only want to see that the set comes back, we want to see that it comes back like on average and not along n, but along some times given by some fixed polynomials that satisfy some natural technical conditions. And we were able to prove the following. So suppose that we have B that is basically, so the density of the set of multiples exists, and that is not barren. So if your set is barren, then there is not much left. So you cannot expect, you cannot really expect recurrence. So, well, maybe you can, but it will be far more complicated to prove. So suppose we have this B, then if you look at the set of shifts of B free integers, then also this is here, so this FB minus R. So this will be an averaging set of polynomial multiple recurrence for almost every R from FB. So by almost every, I mean that there exists a subset of full density such that for R's in the set this holds. And in fact, you can say more precisely what the set D is, but I don't want to do this now.
The same thing with commuting there, or you?
We stopped here, as far as I remember.
Okay.
So maybe an interesting question. All right, so.
Commuting, we don't know.
Okay.
So this was as far as we could go with those methods.
A bit of the epsilon in your theorem.
Okay,
That's your epsilon.
All right, so let me talk about dynamical properties now, like purely dynamical properties. So I want to start with Barron sets, since this is difficult and I don't have that much to say, but nevertheless, there are some things that are important and I want to mention them. So first of all, if B is Barron, it's kind of unclear how rich dynamically the corresponding subshift is. So the main tool I will be playing with later on are invariant measures. And here there is just one measure. This is the Dirac measure at the all-zero sequence. So we kind of lose all nice dynamical tools right away. So what about examples of Barron sets? So the easiest example are just primes. So what is the corresponding set of P3 numbers? This is just a two-element set consisting of plus and minus one. So this can be finite. But once you start changing your Barron sets, things get complicated quite immediately. So for example, if you take semi-primes, then the corresponding set of B3 numbers, this is essentially prime. So, okay, so questions here must be hard. So I think you're all convinced that we shouldn't try to prove to general results with easy methods about P3 sets. And then you can continue. So you can take P3 that will kind of output P2 as the corresponding B3 set and so on. So for example, there was a problem, the following problem. So what is the cardinality of the subshift of prime numbers? And both prime K-tuples conjecture and Dixon conjecture imply that P admissible sequences all lie in the subshift. And since all B admissible subshifts are uncountable, this means that, well, we were believing that also the subshift of primes has to be uncountable. But for a long time, there was no proof. It was given only recently by Tamar Ziegler and Terence Tao. So you can see what kind of questions you're dealing with if you want to study Barron sets. So let me go to non-Barron sets. This will be, well, easier, but I don't think it's less interesting. So there are plenty of phenomena happening here. So Peter Cernak in 2010 suggested to study the B3 system for B equal to the set of square of all primes. Why? Well, the most simple reason you can think of is that it could give us some knowledge about the Möbius function because, well, on one side we have this subshift, this is square-free subshift, but we can also think of a subshift generated by the Möbius function. And the first one is a topological factor of the second one. So if you gain some knowledge about the factor, you gain, well, at least some knowledge about what is happening upstairs. Maybe not much, but okay, let's start with it if it's easier. And the first results for mu squared were as follows. So the first one is that mu squared is generic point for some measure on 0, 1 to z. So basically what you do is you count the frequency of blocks appearing on mu squared. And the second thing is that for this B equal to the set of squares of primes, the square-free subshift is the same as B admissible subshift. And this makes it easier to compute the topological entropy, which happens to be 6 over pi squared. And the last thing I want to mention here is that this subshift is proximal. So if you take any two points, there will exist a subsequence nk such that along the subsequence, the shifts will get closer and closer. Okay, so this was how it started. And then Abdallawi, Maroš Lemanczyk de Delary wrote a paper basically covering Sarnak's program in the Erdős case. So they introduced some language, some ways to talk about it. The results were pretty much the same. So there was, of course, work involved, and it wasn't clear straight away that things will come out this way, but they did. And then during a conference in Toru in 2014, Boszernicz asked what happens for a general B, not necessarily Erdős. So that was just, a short question. We couldn't answer it at all back then. But then it turned out that we, in fact, deal with a rich, interesting class with many new phenomena. So, for example, we first thought that, okay, the square-free system is proximal, so maybe they're all proximal. It turned out not to be true. So there is the following characterization of proximal B3 system, namely a B3 system is proximal if and only if the all-zero sequence is in there. And this happens if and only if B contains an infinite pairwise coprime subset. So I would say pretty nice. So you take your B and you know right away if your subset will be proximal or not. Proximality is a notion kind of opposite to minimality. So what is minimality? We say that a topological dynamical system is minimal if there is no non-trivial closed invariant subset. And the only system that is both minimal and proximal, this is a one-point dynamical system. So this is quite easy to see. So if x and tx are proximal, you get a fixed point, and then two fixed points cannot be proximal. So we were done. And then it turned out that we can also describe when B-free systems are minimal. So this can happen in this world. So on one side, we had proximal examples. There are also minimal ones. So X eta is minimal if and only if eta is a peptide sequence. This means that if I look at my eta, if I pick any position I want, I will see that it is repeated along an arithmetic progression with some difference. And this difference depends which place I picked. So it's not periodic, but it has some flavor of being periodic. And since all zeros on eta are always automatically periodic because they come from this MB, which you just need to check if B-free numbers are periodic. And there is one more condition here. So X eta is minimal if and only if B does not contain a scaled copy of infinite pairwise coprime subset. So you can see this. So in terms of set B, so this also shows you that minimality and proximality are kind of far from each other with a similar formulation.
So what happens if you don't contain an infinite set, but you contain a scaled infinite set?
No, but this is about scaled infinite sets.
Yeah, so suppose you contain one of those.
Then you are not minimal.
But you're also not proximal, so you're something.
Yes, you are something in between. Okay, so let's see, maybe what I say now answers. It doesn't answer your question directly, but it will show you more what these systems are like. So they might be minimal, proximal, or something in between. And even if there is something in between, there is some kind of minimality involved, namely they're essentially minimal. So each of them contains a unique minimal subset. And in fact, we know more. So this minimal subset is again a B-free system. So there is some B star and then FB star and eta star corresponding to this B star, such that this sits here and this is the unique minimal subset. And there is a way of constructing this B star. So what do you do? You start with your B, you look at the scales of infinite pairwise coprime sets that sit there with this scale. You add these scales and then you make your thing primitive. So this is how you produce B. And for example, for any Barren set, this B star will be just a singleton. Okay, so if we want to understand these systems even better, we need to understand what happens in the Teplitz world. So Teplitz sequences can be like the first thing you can say about them is whether they're regular or not. So a regular Teplitz sequence is something which is nice and good and easy to describe. So for example, they are uniquely ergodic. And this is when, okay, so Teplitz sequence, it's a sequence where every position is periodic. So now you can give a restriction on how large periods you want to see. And for some positions, it will be sufficient and for some not. So you look at all these positions for which this is sufficient, you look at the density of these positions, and this has to go to 1 if you want a regular Teplitz sequence. And it turned out that B-free Teplitz sequence can be both regular and irregular. So there will be definitely two cases. The first one easier to control, the second one, well, we don't know that much what's going on there yet. All right, so what about invariant measures? Because I told you when I was speaking about Barren sets that I'm missing this tool, so what do we have for non-Barren sets? So the crucial result here is that of Davenport and Erdős. If you look there carefully, if you look at what is happening there, it will turn out that every sequence nk that it's realizing this lower density of MB is good for finding frequencies of blocks. And along the sequence nk, eta is generic for some invariant measure called Mirsky measure. And then Peter Sarnak asked, what about all invariant measures? I mean, if you have one, it's not so much, right? Especially that this measure is of zero entropy, has discrete spectrum, so it doesn't detect too much of the dynamics happening there. So this question appeared first in the Erdős case, where your B-free system is hereditary. So I was hesitating whether to write x eta here or x eta tilde. I mean, it didn't matter back then, but as you will see, it does matter quite a lot. So, okay, so suppose we have this equality. So to detect invariant measures, you need to look at frequencies of blocks in longer and longer windows that are kind of traveling on your sequence eta. Okay, that's a way to find invariant measures, but doesn't tell you much what they are, right? It's like a theoretical tool that it's hard to apply. You want to describe all invariant measures. However, there is a way to produce more invariant measures once you have this one. So you have this map M, coordinate-wise multiplication. So if you look at the image of B-free system times 0,1 shift, this lands in the hereditary closure. So if I take some invariant measure here, and I know one, if I take, well, whatever I want here, and I join it in whatever way I want, maybe the product way, if you don't have other ideas, but there might be more ways to join these two measures. I take the image via M, I get an invariant measure on the hereditary closure of a B-free system. So I can keep producing more and more measures. And it turns out that's it. So you cannot get any other invariant measure. Every invariant measure on the hereditary closure of a B-free system is of this form. Okay, so I mentioned tautness when I was speaking about number theoretic roots of this subject. So let me convince you now that it's also an important notion from the dynamics point of view. So, and this goes to Joanna's question at the end of the slide. All right, so if I have a set B, whatever set B I want, there exists a unique taut set B prime such that the Mirsky measures coincide, and we have some more properties. So the sets of invariant measures will coincide, and also there is a way of writing explicitly what this B prime is. It's kind of similar to writing what B star is. So in B star, we were looking at rescaled copies of infinite pairwise coprime sets. And here we were looking at rescaled copies of Barron sets. So it has exactly the same flavor. Okay, so applications. So suppose I have B and B prime that are taut. Then the corresponding B admissible sets, or if you want B free sets, this is also true. The corresponding B admissible sets are equal if and only if B is equal B prime. And this happens if and only if the Mirsky measures are equal. So first we have this in the Erdős case. And in fact, already this proof was quite involved. So this used the intrinsic ergodicity of the B-free subshifts. I will talk more about it in a second. And then when we started looking at general sets B, it turned out that is true for taut sets. Okay, so what about entropy and intrinsic ergodicity? So suppose I have a subshift living in the space of 0,1 sequences, then the topological entropy is a quantity that detects the complexity of blocks. So I'm checking how many blocks of length n I see. I take the logarithm, divide by n, and pass to the limit. So that's the definition. Another way to look at this is via variational principle. So apart from topological entropy, we have also measure of theoretic entropy that I'm not going to define, but there is the following relation. And for subshift, there is always some measure realizing topological entropy. The interesting situation is when there is only one measure of maximal entropy, and we say then that X is intrinsically ergodic. So the result for B-free system is as follows. The hereditary closure of B-free system is always intrinsically ergodic. We can say what the measure of maximal entropy is, and we can compute the topological entropy. So we'll see many names here, but it wasn't one paper. So this happens throughout the years. So first, Peckner did the square-free case, and then we had Eddash case, and then at the end, the general case. Okay, so what are main tools? This will be fairly simple, what I say here, but if you look into the details, it's not that simple after all. So we use finite approximations of B. This gives you periodic approximation of your B-free sequence, and this gives you periodic approximation of the Mirsky measure that you have in terms of weak convergence. Okay, so yes.
What was the generality in that theorem? Is this for any?
For any B.
And what if you consider x eta instead of x tilde?
Wait, I will get to this. That's quite recent.
And one more question, this
Yeah.
M here, this is just the pointwise multiplication.
Yes.
Okay.
Yes, M, like plain M is always coordinate-wise multiplication. All right, so recently it turned out that these phenomena are actually more general than we thought. So it's not like specific to this B-free systems. So I need a definition. A subshift X is a convolution system if its sets of invariant measures look like this. So M is again the coordinate-wise multiplication. Here I don't have the Mirsky measure, but just some measure. And that's it. So if the set of invariant measures look like this, I say that my object is a convolution system. And we were able to show the following. So the easy things are that this measure mu is unique, it is ergodic, and in fact, this is the unique measure of maximal density in the system. We call this measure the base measure. And what I told you earlier was actually that the hereditary closure of a B-free system is a convolution system. And we have the following. So
Joana, what is maximal density?
maximal density, you just measure the, this is mu of block consisting of 1.
Why the name convolution?
Oh, because we were working in probability context and somehow it came up there.
Okay, thanks.
There is this multiplication. I don't know, if you have a better name, you can tell me because that's not published yet. All right, so whenever you have a convolution system with 0 entropy base measure, then your system will be intrinsically ergodic. The topological entropy will be equal to nu of 1, and you will know the measure of maximal entropy. So this is somehow like in the reverse order to what happened with the results on B-free systems, because first we had intrinsic ergodicity for square-free system, and we started to investigate, and at the end we decided we know what the structure of invariant measure is. But actually, like the core here is the structure of invariant measures, and this gives you the intrinsic ergodicity. Well, you have to work, but it follows from the structure of invariant measures. Okay, so what about X eta? X eta has X eta star as its unique minimal subset. So in order to control invariant measures on X eta, we need to control invariant measures on X eta star. That's quite clear. So let us make a natural assumption that eta star is a regular Kaplan sequence. So for now, we cannot do much without this extra assumption, but it's a natural one and it covers quite a wide class of systems. So in that case, eta star gets periodic approximations, but from below, such that the corresponding measures generated by these points converge weakly to the Mirsky measure nu eta star. And recall that we always have this approximation from above given by the Davenport-Erdős theorem. So now we are in the situation that you can approximate x eta from above. We can approximate eta from above, eta star from below, and somehow we build a descending family of subshifts that gives us that at the end. So what Keller proved was that x eta is also in a sense hereditary, not completely, but you see there is this lower bound, upper bound, you take the sheets and you take the closure. So it has similar flavor. And he had a conjecture on the form of invariant measures on x eta. It didn't look like this, but I believe it was close enough. So when we were trying to prove, well, we did prove what he conjectured, we came up with this, and I think this is nicer. So let me tell you about this. So suppose eta star is a regular template sequence, then the set of invariant measures look like this. So what is the difference between this and x eta tilde? So there are two main differences. The first one is that I have n, not m. And the second one is that I have 3 coordinates, not 2 coordinates. So what is n? N is no longer the multiplication, but well, it takes some convex combinations of the first 2 coordinates given by the third coordinate. And what is on these 2 coordinates? So this is a specific joining of 2 Minsky measures. So this is the weak limit of such a sequence. And so not only we describe invariant measures, but we also prove that x eta itself is intrinsically ergodic. You can compute topological entropy. You can say what this measure of maximal entropy is, and so on. And again, this is something that is in fact more general. So you can define biconvolution systems. Maybe there is a better name, I don't know. So these are systems for which the set of invariant measures look like this. So there is some measure rho living on 2 coordinates, such that all invariant measures are images of these joinings of rho with whatever you want via n. Now if x is it should be biconvolution system, then there exists a measure rho satisfying the above that is sitting above the diagonal. That's not quite obvious. So this is true for B3 systems, but you might come up with another measure rho, maybe, I don't know. So we call each such rho a base measure. So unfortunately, we don't know if this measure is unique. We weren't able to prove this so far. However, its marginals are unique and its marginals are ergodic, and we know what they are. So this is the measure of maximal density, a measure of minimal density. Okay, so if eta is a regular template sequence, what I showed you on the previous slides was that xy is actually a biconvolution system. And as you can guess, there is a similar result to that for convolution systems, namely that if you have such a system with 0 entropy base measure, then it will be intrinsically ergodic, you know what the topological entropy is, and so on. Okay, so finally I'm going towards thermodynamical formalism, at least a little bit. So what is Gibbs property? So suppose we have an invariant measure. We say that it has Gibbs property if there exists a constant A that gives us such a lower bound for all blocks of positive measure nu. So actually, if this holds, there will be also an upper bound. So what this property means is that all blocks of the same length have approximately the same measure. So what is the motivation to study this property? So first of all, for many natural classes or classical dynamical systems, like sophic systems, systems with some specification properties, there will be a unique measure of maximal entropy, and it will have either this Gibbs property or some modification. So people do different things. It's like there are different variations, but there will be something of this flavor. And another thing is that there is a following result of Benji-Weiss, namely if you have a measure that has Gibbs property, that is a measure of maximal entropy, then there is no other measure of the same entropy. So this could be a way to prove intrinsic ergodicity. We already know that these systems are intrinsically ergodic, but maybe you could take this path, but this is not true. So Pechner proved in the square-free case that the measure of maximal entropy fails to have Gibbs property. And he asked if the same is true for all B. So his proof really used the fact that B is the set of squares of primes, but it turned out that you can extend using different methods. Okay, so what about topological pressure? So suppose I have a subshift, and suppose that I have a function from X, let's say real value. So topological pressure is defined in a similar way like topological entropy. But instead of counting the blocks, I need to take into account the value of my potential along pieces of orbits. And there is also a variational principle similar to the one for topological entropy. So that's one way to define topological pressure. So the other is if you happen to have a Gibbs measure corresponding to the potential, which means that there will be a constant C and P such that, oh, this holds. So this is a condition that resembles the previous one, but involves the potential. Then this P here must be the topological pressure. Okay, so what's the simplest possible potential? That's the potential depending on one coordinate only. And actually, this is the only simple thing that you can do here. So this doesn't go much beyond computing the topological entropy. And the result is as follows. So for any B and for any such potential, you have the following formula. And there is just one equilibrium measure. So just one measure realizing the supremum in the variational principle. So what this formula means? Well, for the full shift, we have just this part. Here appears D, which is the density of ones on your sequence eta, and there is this other part where you need to account that you have, well, approximately y minus D zeros on your sequence. And again, this is more general, so you don't need a special structure of B-free systems here. So you can do this for either convolution systems or biconvolution systems. This will work. So let's complicate the situation a little bit. Let's consider a potential that depends on two coordinates. So let me comment first. Okay, so with each such potential, we associate the following matrix given by the values of the potential. And there are two possibilities. So the first one is when the determinant of this matrix is 0. And then it turns out that for any subshift, you are back to the previous case. So this is a fairly easy observation. So you define psi of I as phi of II, and then you use the following relations. That's it. So this is not interesting. The interesting things happen when the determinant is not 0. So let me comment here on the full shift first, so that we can start looking for tools that could work in the B-free setting. So it is classical that for the full shift, the topological pressure is the logarithm of Perron-Frobenius eigenvalue of this matrix. And actually this method works for all finite type shifts. Okay, so B-free systems are not finite type shifts, but it's kind of close. Why? So we have these periodic approximations of the characteristic function of B-free systems. And if you take the hereditary closure of this, it won't be a finite type subshift, but it will be a factor of finite type subshift. And you can write down explicitly how to construct this. What is more, the fibers will be finite. So there is some space to compute things. The problem is that the associated matrices, they grow like this. And okay, you can look at the eigenvalues, but you cannot really do much more than like 2 steps, maybe 3. You know that the logarithms of these eigenvalues will converge to something. You want to know this something, but there is, so, okay, I see no way to find relations there. So that's not a path you want to follow, unless you're better at algebra than me. Okay, so second attempt, how else can we attack this problem? Okay, so this is the formula for the topological pressure. And since our potential is bounded and depends on 2 coordinates only, instead of looking at this co-cycle, I can just look at the blocks of length n, put a 0 in the beginning and in the end, and compute this other expression. So when you pass to the limit, there is no difference. So let us denote this sum by z and 0, and a similar sum with 1 in front by z and 1. So z0, 0, let's put 1, z0, 1, 0, and we get the following relations. So since we can decompose M with such a diagonal matrix in the middle, we get a formula for z and 0 pretty right away. It looks like this. So there are some constants C1, C2 that depend only on the matrix. So they depend only on the potential. And if you plug this in here, you arrive at the logarithm of lambda class. Okay, so what happens for B-free systems? So this is the formula. Actually, there are two formulas. So the first one, it's a convex combination of these logarithms of quantities that appeared on the previous slide. This is what it is. It's hard to interpret this, right? So you just get some sums. The second one is more interesting. So the first ingredient is the same as for the full shift. The second one is linear with respect to D. And the third one, well, it's something like this. So what are these BL zeros? So BL, this is a block that consists of 0 and then L minus 1 consecutive ones. So how to get there? So first we do reduction to finite sets B. That comes from the fact that we have this descending family of subshifts such that the intersection shares the invariant measures with the hereditary closure of the B-free system. And second of all, we need to find out the formula for a finite set B. So in this case, eta is periodic. So let S be the period of eta. So if you look at your, well, actually almost at the definition. So this is what the definition gives you. Then you are allowed to replace this with this. So that's a similar trick we did before. And then these ends cancel out. So you're left with a finite sum. And now, if you write the smallest part of eta that repeats into both directions, what does it look like? It has some zeros and it has some ones. So we can interpret it in the following way. So the zeros are where we cut. So this is built out of the pieces like 0, some number of ones, 0, some numbers of ones, and so on. And now each block that sits underneath will have these zeros inherited from eta. So there are S times 1 minus 1, 1 minus D zeros like this. And the remaining positions can be filled in any way you want. And I told you about this cutting into pieces, and this is exactly what happens because your potential just see two consecutive coordinates. So you can really cut and these things behave independently. So this is what you get. And now if you start looking at what the length of these cutted blocks are, so you will see like a block of length 2, some number of times, a block of length 3, some number of times. So this is here. And it goes to the front thanks to the logarithm. And if you interpret this, you will realize that this is nothing but the Mirsky measure of this block. So this is how you get the first formula. And for the second formula, well, we know already what ZL0 is. So if you plug this in, you get the second formula. So, okay, so this is what our formula looks like. So the first ingredient, this is something that is constant. The second one is linear. What is the third one? Can we say more about this? So what happens to the third term when your hereditary closure B-free system more and more resembles full shift? Does it behave correctly and at what speed? So that was a question that we asked. And in order to answer, I need to tell you what, so how to interpret the word resembles. So one could naively think that this is just looking at the language. This doesn't work. You need to look at the density of ones. So we want a result for D converging to 1. And it turns out that this third ingredient is less or equal than a constant time 1 minus D to epsilon for any epsilon in the open interval 0, 2. So what is bad about this result? This part within the family of F sets. So this is really a strong assumption on the set B, and we weren't really able to get rid of this one. So that's an open question here. I have like 5 more minutes. So let me tell you a few words about the proof. So these are the main 2 tools that we have, and this is really related to the F case. So D, this is the Mirsky measure of block 1, and this is the formula for it. Okay, these blocks B, L0 also appear there, so we need to control their measure. It turns out that this is bounded from above by such a sum, so this is equal to S squared, where S squared is the sum of reciprocals of all B's in your set B. So that's one thing. And the second thing is that this sum S is morally the same as 1 minus D. And once you know these 2 little things, you can look at this sum and split it into 2 parts. We split it at L0, that is approximately 1 minus D to minus 2 plus epsilon. And then we estimate each part separately. So the first part gets constant times 1 minus D to epsilon as the upper bound. And the second part goes to 0 with polynomial speed for any polynomial. So this is more or less how it works. And then the question, what happens for general B's? I don't know. Okay, so thank you for listening.
Okay, we have some time for a few quick questions.
Do you have a theory in multi-dimensions? Like it's not Z action, but Z to the N actions where there's
Problematic already at the level of invariant measures. So the problems appear much earlier if you want to do like invariant measure in multidimensional settings. We tried some years ago and that was hopeless.
There's a question here.
Let me ask you about some of the earlier results that you've stated. So you had these results that shifts of B-free systems are good for polynomial multiple retardants.
Yeah.
There's some conditions on the B-free system. So does this include also square-free?
Yes, it includes all B-free systems.
Is there any intuition for why this is the case?
Like the amount of periodicity that is sitting there. So it falls into a more general scheme of so-called rationally almost periodic sequences, so or sets that can be approximated by periodic things.
There was another earlier result which was about shifts of finite subsets of A, the admissible ones, appearing with positive density again.
This one?
Yes. Yeah, and you said there are some dynamical ingredients that help you prove that. I was wondering if you could say what those are.
Yeah, so for example, you need to know that the support of invariant measure, the support of Mirsky measure is everything. And then you will know that this pattern will get repeated on eta. And this is true for a taut set. So first we had like another condition easier to deal with, but later it turned out that Mirsky measure is of full support for taut sets.
And so that the same statement holds for any kind of B3 sets.
Not for any B3, but under some assumptions. So you need them to be like taut and probably proximal, and then it works.
Okay.
Any other questions? All right, let's go ahead and thank our speaker.